Thank you everyone for being here. It's great to see so many people here to talk about fun maths. So as Matt says, I'm a PhD student at UCL, which looks like this in lots of photos, although it's normally much more rainy than this. An interesting fact between me and Chris, who spoke before me, Chris said he got up at 5, I got up at 5:20, which means we've both been awake for 395 minutes before starting our talks. So we're on equal grounds to begin. Okay, so today I'm going to be talking to you about MENACE, which is something I first read about, like so many things you'll see this week, in a Martin Gardner book. And MENACE stands for Machine, Educable, Noughts and Crosses Engine, which I think is a really great acronym. And this is, so Machine Educable is kind of like machine learning. So this is a machine learning machine, which I'm going to use to explain to you how machine learning works. Because recently, for example, here you can see the World Go champion really annoyed with himself for losing to Google. Machine learning has been in the news a lot, so I'm going to explain to you some simple techniques in machine learning and how machines actually do this learning. But I'm not going to explain through Go, because Go is a very complicated game, as some of you might know. I'm going to explain to you through an easier game, Noughts and Crosses, like the name suggested. And I'm going to explain to you how to make a machine learning robot that can play Noughts and Crosses and can learn how to play Noughts and Crosses. And this was first built by this man, Donald Michie, in the 60s. So Donald Michie had worked at Bletchley Park during the war. He'd worked on the Tunny cipher. And his main interest, though, was in biology. So he was interested in computation and biology, which got him interested in how machines could do learning to mimic animal learning. And this led him to build MENACE to kind of demonstrate that this could be done. And he built it in 1960 before computers were so widely available. So it looked like this. That is 304 matchboxes. You can see here he's writing Noughts and Crosses on a bit of paper. He's got one of the matchboxes open, which has some counts in it, which you may or may not be able to make out. And you almost certainly can't make out that each box has a possible position in Noughts and Crosses drawn on it. So he must have spent a long time doing this. He then played a tournament against it, which took a whole weekend to play 200 games against this thing. It was a big undertaking, but this machine learns how to play Noughts and Crosses. And I'm going to explain how with an example game. So, first of all, MENACE always goes first. So you could build a MENACE that goes second. To reduce the number of matchboxes, Donald built MENACE that would always go first. And how you play a game against MENACE is, first of all, you find the matchbox which has the empty board on it. Then you give the matchbox a shake, you open it up, and you see which token falls to the front. And in this case, it's the red one, and red is code for going here. So now it's the human's turn, and I decide to go there because I think the middle's a good square to go up. So it's MENACE's turn again. So again, you look through your 304 matchboxes, and you find the one with this pattern on it, which is that one. I should say here, of course, MENACE doesn't really care if you've rotated it. It would in fact be silly to make different matchboxes with all the rotations and reflections. So you have to sometimes rotate the board to make sure you find the right box. Again, you shake the box, you open it up, and you find a blue token. And blue token is code for going here. Human players go again, I go there. It's MENACE's turn, so again, look through all my 304 matchboxes. I find this box, I give the box a good shake and open it, and it's a green token, and green is code for going there. So it's done quite well there. Human go goes there, so human is looking like it's doing really well. So this is against MENACE before it's done much learning. This is quite a young MENACE. And the learning comes later and it will not make these mistakes again. So MENACE again, you find this box, you shake it, you open it up, you get a orange token. Orange is code for going there. I go there and I have 1. So this, as I said, this is a young MENACE that's not very good yet. But now is where the machine learning comes in and we teach the robot to do better. So because it's lost, these were bad moves to make. So we take away that, I went a bit quickly, we take away the orange token and we put that box away. So now it's less likely to go where it went orange because that might have been a bad move. Similarly, we take away the green token and we put the box away because green may have been a bad move because it led to losing. We take away the blue token and put that box away because blue could have been a bad move. And we take away the red token and put that box away. So now, next time we play the machine, it's less likely to make these mistakes it's made again. Obviously, there's more than one of each colour in these boxes, so it's not impossible because like if the second move was bad, the first move wasn't necessarily bad, but it's less likely to make these mistakes again. So we've beaten it. If it wins against you, so if MENACE wins, you give it 3 more Bs of each box. So if it wins, you encourage more behaviour. And if it draws, you add 1 B to each box, because if you're playing a perfect human at Noughts and Crosses, it should actually never win. So you have to incentivise drawing because it is better than losing. And if you follow just these simple rules with your matchboxes, over time it improves. So this is a graph from Donald Michie's paper he wrote about this, where this is the change in the number of beads it has over time. So you can see at the start he beats the lot, so the number of beads decreases, and then it starts picking up a lot, and eventually it's going in an almost straight line because he is drawing every time. So there's a few interesting things you can point out here. Here, 20 games. So after about 20 games, it's fairly flat. So it's winning and losing, or drawing and losing about an equal number of times. And then after about 40 games, it gets very good at drawing. Here, there's an interesting thing. So these boxes with arrows represent when he varied his game. So he realized that actually if he'd been playing, up to that point, he'd been playing a perfect strategy against it. But he realized that actually if he played less well at noughts and crosses, he'd get MENACE to use some boxes that it had not trained on before. So he'd find some boxes he'd never opened before. So here, he changed his strategy to a less good strategy, found that MENACE hadn't actually learnt to beat him, but then about 20 games later, it picked up and managed to start beating him, and actually beating him rather than just drawing on these boxes, which shows just how quickly this very simple machine can learn to play noughts and crosses, which is very cool. I'm going to talk a bit about some other games you could apply this to kind of show you how complex some games are. So for example, you think noughts and crosses, 3 and 4 matches, not bad. 3 and 4 matchboxes, not bad. So how many matchboxes would I need to make a machine equivalent to play Connect 4? So in Connect 4, there are this many 4 trillion possible positions, which would mean you would get this many meters cubed of matchboxes. Good way to visualize this, if you put those matchboxes in a sphere, then the radius of that sphere would be the height of the Eiffel Tower. So already Connect 4, which you think doesn't seem that much more complicated than noughts and crosses, already it's very, very big and difficult to solve this way. But you can just about get a computer to store all of this if you don't do an actual matchboxes, if you do it in a hard drive. So Connect 4, you can almost use the technique, but you kind of need to improve things. So let's go even more extreme, chess. Does anyone know how many different possible positions there are in chess? Around 10 to the power of 43, which leads to 10 to the 38 meters cubed of matchboxes. So again, if we imagine a sphere, which is 10 to the 38 meters cubed, we've gone a bit. If the sun's at the center of that sphere, then Mars is just engulfed by that sphere. I'm having the same problem. There. So again, very complicated. And this is why chess was very difficult to beat computers at. It was actually beaten in the 90s by a robot, but the robot Deep Blue that beat Garry Kasparov in the 90s wasn't actually a machine learning robot. At each position, it kind of looked at the possible moves 2 or 3 moves ahead, used some clever maths to decide which of those to carry looking further. And so it kind of looked at enough of the possible combinations from where it currently is to do that. So it didn't actually have to look at all the different positions. So that was worked differently. But the interesting one from machine learning's point of view is Go, because this is the one that was beaten recently. So Go, if you haven't played Go, it's a really, really good game. And it's estimated that there's about 10 to the power of 170 possible positions in Go. Which, if you were to make a matchbox for each one of those positions, that's going to be 10 to the 165 meters cubed of matchboxes. So again, let's put them in a big sphere. And the observable universe is like a tiniest part of a pixel in the middle. You can actually fit 10 to the 27 universes side by side along the radius of this cube. To really emphasize this, like chess is a tiny proportion of the observable universe. It was just like from the sun to Mars. And this is how much more complicated Go is than chess. It's 10 to the 27 plus whatever fraction we are of the whole universe. So this is why it was such a mind-blowing thing that computers have beaten Go, because obviously you cannot program a computer to look at all these combinations. So you have to do something more clever. So a few things. I haven't got time to explain how AlphaGo works, and I don't understand all the details of how it works, because it's a very complicated thing. But there are a few things you can immediately notice that you can drastically reduce this number by. So if you think about my original explanation of MENACE, we took a matchbox for each playable position. So if you did this for Go, you'd have a matchbox with that position on, and you'd have a matchbox with that position on. And those positions are very similar. Even if you had never played Go before, you can kind of see that there's not really much, there's no difference apart from it's been moved. So one thing AlphaGo does is, rather than actually looking at every possible position, it looks for patterns of these positions. That uses very similar software to what Google uses for image recognition, and it spots patterns like this everywhere. So it could treat these two very much the same, and in that way reduce the number of possible different positions to look at. Similarly, if you've got this one and you put a kind of a relevant black dot over there, there's very little difference again. So it can pick up that positions like this are very similar. And a few simple ones that allows you to cut the amount of things you need to look down quite a lot, but they've done a lot more clever things and really managed to cut this down a lot. So back to MENACE. If you'd like to play against MENACE, a year or so ago I wrote a JavaScript version of it, so you don't have to sit and label all your 3 and 4 matchboxes. You can go to this page on my website. You can see I took the screenshot at Christmas because there's a Christmas hat on the top of my thing. I've never updated the screenshot. So you've got down here, it tells you how many beads are produced in all the boxes. You play the games over here, you can watch these change, and you can leave it playing as random, so it's quite fun to play a few games against it to see how easy it is to beat. Put it playing against random, go make dinner for an hour, come back, and it'll be really good and beat you most of the time, or at least draw with you. So that's an interesting thing for you to go and play with. But if you have more time than me for making things, you could go away and make one. So this is one, I gave this talk at a conference in Germany last summer, and Oliver, someone called Oliver who was in the audience, I met afterwards, went away and laser cut himself this beautiful box, cut to the shape, got 304 matchboxes, printed off coloured labels, so you've got the first turn box there, the second turn box in this colour, and put beads in all the boxes and made this machine. And he brought it to London to show me, and it was really fun to play against, so I'd recommend making one. I've got as far as buying the matchboxes, but I haven't found time to label them all and put the beads in yet. So hopefully in a few months I might have one of my own. But also, as far as I know, he has not found anything to do with the matches yet. He's got... and the biggest problem with these is that actually inside his machine, he's of course included all the strips you use to light the matches. So he can't even light these matches to use them as matches. He's just got bags full of matches that are utterly useless to him. Okay, so another reason I'm here, as Matt mentioned at the beginning, is Chalkless Magazine. So at UCL, with about 10 other PhD students, we have started this magazine, which we print twice a year, and we distribute to universities, maths jams, conferences like this, and other places across the country. And one thing that, when Oliver I met at that conference, wrote us an article about MENACE, and we have lots of free copies of this in the exhibition hall. So pop by later and pick some up and have a read, and you can learn more about MENACE and more other things. Of course, there's a lot more in there. We've got our Agony Uncle, Deirdre Richelieu. We have got the top 10 calculators, which is bound to cause some arguments here. And we've got what's hot and what's not. Hopefully the 40 minutes conference noise isn't relevant to this conference. But they are not hot, obviously. And lots of more fun stuff. And it's a really fun project to work on. And we really like distributing it. There's also other articles. There's a cross number, which is like a crossword, but with numbers, which I write and is notoriously difficult to solve. But it's really fun, so you should have a go at that. Last weekend, we just finished work. In fact, yesterday, we were correcting typos. We're just putting the finishing touches to issue 4, which will be out in October. And you're the first person I'm getting to show the cover to. So this is going to be the cover of issue 4 of Chalk Test. And I can tell you a few of the things that are in there. So we've got, so this cover picture is a picture owned by the UCL Art Museum, which there's more details about inside the magazine once we finally print it. I say it's launching online on the 4th of October, so you've got a bit to wait before you can read this. And there's some really nice articles in here. James Grime has written about the actress who invented Wi-Fi. Colin Wright he's not on the cover, but he's written about the doodle theorem for it, which is really cool. We've got a proof by storytelling article, which does anyone remember the children's series Old Bear? That's a shame. We've been allowed to use pictures from that TV series, and the author gave us permission, which is really cool. And also got problem solving, which has lots of problems and explains different problem solving methods. Some prime jewelry, which is kind of making bracelets out of some prime numbers. And as I said, it's launching online on the 4th of October. We're having a launch quiz on the 11th of October in the evening, so if you're in London then, follow us on Twitter or sign up to our mailing list or tell me and I'll email you and you can come along to that. And I will hopefully see lots of you there. And I'll talk to you lots in the exhibition hall where we'll be giving out lots of the issue 3, the one before this one. And that is all I've got. Thank you for listening.